Welcome. In this video, we'll look at the graphs of trigonometric functions and think about how we can use our ideas of inverse functions to define the inverse trigonometric functions, the inverse sine, the inverse tangent, and the inverse secant. Here we have a graph of each of the four basic trigonometric functions. We've got sine and cosine, and then the tangent and the secant. We're not including the cotangent and cosecant. They're reflected and shifted versions of the tangent and secant. In order to think about our inverse functions, we need to think about what it takes to be one-to-one. And in particular, notice that none of these trigonometric functions are one-to-one because they all fail the horizontal line test. The horizontal line test says if you take a horizontal line, a one-to-one function can only cross it in at most one point. So for example, if I drew a horizontal line above the graph, notice here it doesn't cross at all. That's not a problem. But if I cross anywhere inside the range, I'm intersecting at infinitely many different points because of the periodicity of our functions. So these functions, the trigonometric functions, are not invertible. But what we want to do is we want to find restrictions of the functions so that they are invertible. The way that we'll do this is we're going to choose a subdomain, an interval or intervals on which the function is invertible. And we're going to adopt the following idea. Each of the trigonometric functions are defined in terms of the unit circle. So if I were to draw the unit circle so we can talk about our quadrants, we're going to define our trigonometric functions, our restrictions, so that they always include the first quadrant. And then we're going to extend the intervals either to the right or to the left so that we continue to be one-to-one. So let me illustrate that with the sine function. The first quadrant goes from the angle 0 to the angle pi over 2. So here's the angle 0 to pi over 2. And on the graph, 0 to pi over 2 corresponds to the maximum value of the sine function. And so if I go from 0 to pi over 2, I get this is the first quadrant. Now, I want to extend this so that I get a one-to-one function. If I keep going to the right, notice that now I'm failing the horizontal line test if I keep going that direction. So I cannot go past this maximum. As soon as I start to go down, I fail the horizontal line test. So instead, I'll extend in the other direction, and I'll go until as far as I can, which will be the minimum value. And so I go to negative pi over 2. Okay. And so for the sine, its restricted domain corresponds to quadrants 1 and 4, which is allowing me to take a restriction from my domain going from minus pi over 2 to pi over 2, including the endpoints. All right, let's move now to the cosine function. Again, let's quickly draw our unit circle so we can think about where we are. We're always going to start in quadrant 1. And so quadrant 1 for the cosine, we start at a value 1 and we go towards 0. So I start at a value 1 and I go to a value 0. And so quadrant 1 corresponds to this first piece of the cosine function. Now, we want to extend this so that we get the entire range. Notice we already have the highest point. We go down. And the easiest interval to continue is to go all the way to the minimum, which happens at an angle of pi. So here we go to the angle of pi. And so my restricted domain goes from 0 to pi. And again, we get to include the endpoints. And this allows me to go from 0 to pi. Notice that this is quadrants 1 and 2 of the unit circle. So I've got quadrants 1 and 2 of the unit circle. And this is my restricted cosine that has it has the full range. I go from minus 1 to plus 1, but I only repeat each y value once. Our third example is the tangent function. Let's quickly think about our unit circle. So we have our unit circle, and the tangent, we're wanting to do the first quadrant, and recall that the tangent measures the slope. So in the first quadrant, I start at a slope of 0 and I go through these values, but notice that I cannot include the angle pi over 2. And that's because my slope's undefined. You can't define the tangent, and that corresponds to the location of my vertical asymptote at pi over 2. And so the restricted domain in the first quadrant includes this first part of the graph. So how could I extend it? I could extend it by continuing on and going until from pi over 2 to pi. So I could actually, I can't use this point again. That is a valid extension of the tangent function, or a restriction of the tangent function, and it would be 1 to 1. That would correspond to continuing this graph. The problem is that this creates a discontinuity in my function, and so it's not actually a very satisfactory choice. So let's go back and undo this for a second. Instead, what makes more sense is to extend it in the other direction, and so go backwards into quadrant 4. And if I do that, I get from minus pi over 2 to pi over 2. Notice that I can't use either of the endpoints. They're corresponding to my vertical asymptotes. So my restricted domain for the tangent goes from minus pi over 2 to pi over 2, not including the endpoints. For the fourth example, we're going to focus on the secant. And recall that the secant is the reciprocal of the cosine function. If I thought about my unit circle and thought about where my quadrants were, I start in the first quadrant, and I can't divide by 0, so I cannot include this point. My first quadrant will start at the angle 0 and go to my vertical asymptote. Okay. Now, what do I do now? The tangent, we went to the left so that we could be continuous, but for the secant I cannot do that because I will be failing the horizontal line test. One possibility to continue our restriction is to go to the other side of the vertical asymptote and continue until we reach the value of pi. And this has a disadvantage of being discontinuous, but there's not a way of doing a continuous version for the secant. So what is a restricted domain? We start at the angle 0, we go to the vertical asymptote, we skip over the vertical asymptote, and then we continue until we reach pi. Let me finish the unit circle. For our secant, we get the quadrants 1 and 2, and because the secant and the cosine are related, notice that the domain is essentially the same for the restricted domain, except the cosine is 0 at the angle pi over 2, so we can't define that point at for the secant. We're going to use these restrictions to define our inverse trigonometric functions. So the sine, when it's restricted from minus pi over 2 to pi over 2, and recall that on the unit circle, this corresponds to quadrants 1 and 4, including the ends. So the domain is from minus pi over 2 to pi over 2, but the range goes from minus 1 to plus 1. The inverse sine is the function that goes in the reverse direction. So the inverse sine takes a value from minus 1 to 1 and gives you back a value that's between minus pi over 2 to pi over 2. The idea of an inverse function says you give me a y-coordinate on the unit circle, and I'll give you back the angle that will give you that value. So if you tell me a y value on the unit circle, the arc sine will give me the inverse function. And I just used a word here. Another name for the inverse sine is the arc sine. And it's often written as a sine of x or arc sine with arc sine. Those are other ways of writing that function. This is the a sine is the most typical one used on a calculator or a computer program. Okay, so let's move on to the arc cosine, the inverse cosine function. Remember that our restricted domain is the top half of the unit circle, quadrants 1 and 2. We're including the endpoints. The inverse cosine function takes values from -1 to 1, the range of the cosine function, and gives me back an angle corresponding to something between 0 and pi. Again, the idea there, it takes an x-coordinate. So this is an x-coordinate on the unit circle. For example, I might start with an x-coordinate, and the arc cosine gives me back the angle between 0 and pi that gives me that x-coordinate. And again, I use the language again, the arc cosine is the same function as the inverse cosine function. The tangent is defined from -pi/2 to pi/2 is my restricted domain. So I don't get the endpoints this time. And so the inverse tangent function, also called the arctangent function, will take a slope, and the slopes are possible from any real number, so this is a slope, and it will give you back the angle from -pi/2 to pi/2 that will give you that slope. Our last example of an inverse trig function is the arcsecant, or the inverse secant function, and the domain restriction for the arcsecant is similar to the cosine, except you cannot use pi/2. So it's the top half of the unit circle, quadrants 1 and 2, and the inverse secant, or the arcsecant, what are the possible values? Well, they're the reciprocal of the cosine. So in quadrant 1, we get from 1 to infinity. In quadrant 2, we get -infinity to -1. Notice I wrote it a slightly different way. The order I write intervals doesn't matter, although the way that I write the interval does. Given this value of the secant, the reciprocal of an x value, it will give me an angle that's between 0 and pi/2 for the first piece, or pi/2 to pi for the second piece. So those are my inverse trig functions. And a calculator typically has defined the first three. Your graphing calculators will have an inverse sine, an inverse cosine, and an inverse tangent. I want to illustrate one example of how we use the arc sine function on a calculator to characterize all the angles that solve an equation. So how do I think about this? I've got an example. We want to find all the angles for which sine of x equals 3/5. So if I'm solving an equation like sine of x equals 3/5, then I want to do something to eliminate the sine from my equation. So let's start with what we have. Sine of x equals 3/5. I want to somehow eliminate the sine, and so I'm going to use the arc sine function on both sides of the equation. So the arc sine cancels the sine, and I get x equals the arc sine of 3/5. Now, this only works if x is in the restricted domain. So this is if x is in that restricted domain for the arc sine, which are quadrants 1 and 4, so -pi/2 to pi/2. And we should think about what this means in terms of the unit circle. Whenever you're solving a trigonometric equation, we think about the unit circle. And what does this mean? The sine of x equals 3/5 means I have a y-coordinate on the circle that's equal to 3/5. So I go and I think, well, where are 3/5? 1, 2, 3, 4, 5. There we go. 3/5 is a height on the axis. And I'm looking for a height on the axis. And our restricted domain says we're finding values between minus pi over 2 and pi over 2. So when I solve this equation on a calculator, if I punched into a calculator and said, what's the arc sine of 3/5, it would give me a value. And let me find the decimal value on my calculator. My calculator gives me back a decimal value, because it's not exact, this is an approximation, of 0.6435011. Now, it's important that you make sure your calculator's in radian mode, because we're doing radians. Many calculators by default are in degree mode, so you need to be sure you switch to radian mode. So what does that mean? It means, so here's my origin, here's my angle 0. If I travel a distance of 0.6435 along the circumference to get an arc, that's my radian angle. I get an angle of 0.6435011 something something something. And when I calculate the sine of that angle, I get exactly 3/5. But you can see that this isn't the only solution. And so when I solve these equations, there are multiple solutions, and I need to think about the unit circle to figure out what the other angles are. So one solution is this angle x that the calculator told me. X equals this angle that we found. But what are some others? Well, notice there's another solution on the other side. How can I find that angle? You need to think about symmetry. So if it took 0.6435 coming up from the axis, then it's going to be the same amount coming up from the other axis, and I need to think about what that angle is. Here's where I want to think about angle addition. That angle corresponds to going to an angle of pi, and then coming backwards the clockwise direction by the angle that I found. And so this would be pi minus 0.6435011, whatever that number is. Okay? So now we have two different ways of getting this angle. So this is the angle pi minus theta. Those are the only 2 points on the unit circle, but there are infinitely many turns that you can use to get there. So for example, I'm back where I started if I go theta plus 2 pi, or theta plus 4 pi, or theta minus 2 pi. Those all land me on this first quadrant angle. There are also ways of landing on the second quadrant angle, and that would be x equals pi minus theta plus 2 pi. In other words, 3 pi minus theta, or 5 pi minus theta, or 7 pi minus theta. All of the odd multiples of 7 pi, 3 pi, 5 pi, 7 pi, they all land me on this axis, and so subtracting theta gives me these angles. There are infinitely many solutions, and so a way that I could describe these is I would say solutions look like x equal this number theta that we found, plus on the right I have multiples, even multiples of pi. So I'm going to say theta plus 2 times an integer pi, where n is 0 or plus or minus 1, plus or minus 2, on and on forever, as well as solutions that look like, what are the others? They're odd multiples of pi, and so How do I get odd numbers? That would be a number 2n plus 1 times pi, odd multiples of pi, and then we subtract theta. And again here, n are all the possible integers. So there are infinitely many solutions to this equation, and I find one of them using a calculator, and then I get the others by thinking about the unit circle.